Hello. In this video, we're going to look at how we can use limits to figure out what's going on with asymptotes. So we have three types of asymptotes we're going to deal with, and that is vertical and horizontal, which we've already seen before in previous courses and could theoretically figure out without calculus. But also we're going to deal with slant asymptotes, which are straight lines that are not vertical or horizontal. So let's start with a function where we have f of x equals 2x squared plus 8x plus 6 over x squared minus 9. So first we're going to consider where we would find vertical asymptotes. So vertical asymptotes are generally speaking going to be wherever we have non-permissible values of the domain. So in this case, that will come from the denominator. Now, as you've learned previously, the best practice for working with rational expressions is often to see if we can simplify them, and that involves factoring. So I'm going to actually check to see if I can factor anything here. So I end up with both a numerator and a denominator that are factorable. And in fact, when we do that, in this case, we end up with a factor that is in common between the numerator and the denominator. And that is going to be significant. Oops, sorry, that's not a 2. When it comes to our limit work and figuring out what our asymptotes are. Because as it turns out that in finding asymptotes, we're also finding points of discontinuity if they exist. So our vertical asymptotes are going to potentially be at our non-permissible values for x. So x cannot equal positive or negative 3. So we're going to consider what's happening as x approaches 3 and negative 3. Now I'm going to start with the factor that actually does cancel out. So x plus 3 cancels out here. So I'm going to consider what happens because that does mean that there is going to be a limit as x approaches the associated non-permissible value of negative 3. So the limit as x approaches negative 3 of f of x, which is the whole unsimplified expression, is going to be equivalent to the limit as x approaches negative 3 of the simplified fraction, which is 2 times x plus 1 over x minus 3. And in this fraction, I can simply substitute negative 3, giving me a numerator of negative 4 and a denominator of negative 6, which means 2/3. When the limit actually exists and is finite, what this tells me is that I have a point of discontinuity. So this is not an asymptote because I have a finite limit. Discontinuity at the point negative 3, 2/3. Asymptotes by definition have to involve infinity somehow. So now I realize that what's going to happen at the other non-permissible value, 3, because that one doesn't factor out, that one doesn't simplify, is going to involve infinity. But because my ultimate goal here is curve sketching, I'm going to consider what's happening on the left and the right. So as we approach 3 from the left, and as we approach 3 from the right. And so what I'm going to consider here is that as I approach 3 from the left, well, my numerator is going to basically go to 8 because 2 times 3 plus 1, 2 times 4 is 8. But the denominator I need to consider is going towards 0, but I need to consider, is that a 0 that is slightly positive or slightly negative? So if I take a number that is slightly less than 3 and I subtract 3, I'm going to get a negative number, which means that this is going towards negative infinity. Right away, I know I have an asymptote, because even if one side involves infinity, this is an asymptote. But I want to know the behavior of the function around that asymptote, so I persist. If the value of x is slightly higher than 3, the numerator is still going to be basically going to 8. My denominator is going to be going to 0. But if I have a number that's slightly higher than 3 and I subtract 3, I'm going to get a slightly positive number, which means this side is going to go to positive infinity. Now note, as I was doing this analysis, I was using the simplified form of the fraction to think it through, just because it was easier. But theoretically, you could use the unsimplified form as well. What this means, these two things together, is that I have a vertical asymptote at x equals 3. So the line x equals 3 is a vertical asymptote. And specifically, when I go to sketch it, I know that it's going to look like the function is decreasing on the left. So as I approach 3 from the left, it's going towards negative infinity. And as I approach 3 from the right, it's going towards positive infinity. So that is what I expect to see as the behavior of the function around that vertical asymptote. Now, horizontal asymptotes are about what happens as x approaches positive or negative infinity. So for horizontal asymptotes, we have to consider the limit of this function as x approaches positive and or negative infinity. So for that, I look at the form of the function where I've divided out the highest power of x. Now, in this case, the highest power of x is x squared. So let's look at the limit as x approaches infinity of 2 plus 8 over x plus 6 over x squared. So I'm going back to the original unsimplified form of the function. And this becomes minus 9 over x squared. Because this form allows me to figure out what's going on, each of these fractions that has x as a denominator, so 8 over x, 6 over x squared, 9 over x squared, as x becomes infinitely large, is going to go to 0. And that's actually true whether x is going to positive or negative infinity. So I'm going to get the same thing here. So 2 over 1 is 2. And again, if I analyze this as x goes to negative infinity, of 2 plus 8 over x plus 6 over x squared over 1 minus 9 over x squared, I can see that this is also going to equal 2. So what this means, because there is a finite limit here horizontally, we have a horizontal asymptote at y equals 2. Now, in the case where the horizontal asymptote where the limit towards infinity or negative infinity isn't finite, we might still have an asymptote. So if my limit at infinity goes to infinity, that's when I might end up with a slant asymptote. So let's consider this function here. I'm still going to consider what's happening with vertical asymptotes first. So vertical, because that has to do with my non-permissible values of x, I'm going to consider what happens as x approaches negative 2, because x cannot equal negative 2. So looking at the limit as x approaches negative 2. Now in this case, I'm going to look at the numerator and see, is it going to be factorable? In other words, is x plus 2 a factor of x squared plus 3x minus 5? It is not. So I need to consider the one-sided limits here. So the limit as x approaches negative 2 from the left of x squared plus 3x minus 5 over x plus 2, and the limit as x approaches negative 2 from the right of x squared plus 3x minus 5 over x plus 2. As I approach from the left, all right, so the numerator, I've got 4 minus 6, which is negative 2. I've got negative 7 as the numerator. And I'm going to approach 0 in the denominator. Now remember, because this isn't 0 over 0, I can actually reason it out. Negative 7 over 0, I can reason out. But if I have a number slightly less than negative 2, so in other words, negative 2.001, for example, I'm going to get a slightly negative number in the denominator. Because I have a negative 7 divided by a slightly negative denominator, this is going to be approaching positive infinity. If I then consider what's happening from the other side, my numerator is still going to negative 7. My denominator is now going to approach 0, but this time it's going to be slightly positive, which means this one is going to go towards negative infinity. Because these involve infinity, that means I do have a vertical asymptote. And that vertical asymptote is at x equals negative 2. And more specifically, I know the behavior of that function around that asymptote should be that the function from the left is going towards infinity and from the right is going towards negative infinity. So that's the situation for the vertical asymptote. For horizontal and slant, I basically start out the same way. I consider so horizontal or slant, I consider what would happen if I was going towards infinity. So the limit as x approaches infinity or negative infinity, it's going to ultimately be the same in both cases, of f of x. But what I now consider is that the numerator has a higher power than the denominator. In other words, if I were to divide out the highest power of x, the x squared, what I would end up with is 1 plus 3 over x minus 5 over x squared divided by 1 over x plus 2 over x squared. And now what's happening is my denominator is going towards 0 fully as well. So this right here is going towards 1 over 0, which is not finite. That is infinite. And if it's infinite, then I don't have a horizontal asymptote. I'm not going to worry about whether that's positive or negative infinity at this point, because I'm not going to worry about whether that denominator is positive or negative. It is positive, just FYI. But the situation here is that then potentially I have a horizontal asymptote, or a slant asymptote, sorry. So to find that slant asymptote, I actually do the division. So I'm going to divide out x squared plus 3x minus 5 divided by x plus 2. And I can do that division using synthetic division. So 1, 3 minus 5, negative 2. Your synthetic division process might be slightly different than mine. It's not ultimately all that important how you do your synthetic division. You just need to know how to do division. So what I get here when I divide is that essentially this means that f of x is equivalent to x plus 1 and then a remainder of 7, so minus 7 over x plus 2. That is an alternate form of f of x. It's equivalent to the original fraction. It's just been expressed as a divisor, or sorry, a quotient and a remainder. Well, now if I consider what happens at infinity. So the limit as x approaches infinity of x plus 1 minus 7 over x plus 2. It is still definitely going to go towards infinity. But what matters to me here is that this bit is going to go to 0. So as this function gets closer and closer to infinity, the curve of this original rational function is going to start to look more and more just like the line y equals x plus 1, because that remainder part is going away. So this function becomes more and more and more flat or straight as we get closer out to infinity. And that actually is true on the positive side and the negative side. So what we have is we have a slant asymptote of y equals x plus 1, because this curve starts to basically resemble that straight line as we get further out. Generally speaking, we'll have a slant asymptote. If I go back and look at this original function, we'll have a slant asymptote when the degree of the numerator is 1 more than the degree of the denominator. 1 more than denominator. Because when we divide those, if the difference of degrees is 1, then when we divide them, we're going to get a linear, and then with whatever remainder we have. If I had a difference of degrees that was 2 or 3, then I wouldn't end up with a straight line when I divided. So if your degree of your numerator is bigger than the degree of your denominator, you're not going to have a horizontal asymptote. If it's 1 more, you're going to have a slant asymptote. If it's 2 or 3 or 4 more, I mean, in theory, you could have a parabolic asymptote or whatever, but we're not going to worry about those. In situations where the degree is the same, so 2x squared over x squared, or the numerator has a lower degree, then you will end up with a horizontal asymptote. So the degree is less than or equal to the degree of the denominator. Then you will have a horizontal asymptote.